Yeah, so this is the networking tutorial that Jamal kindly invited us to give to the networking kernel world. So Weston has been working on for well a few years now on different kinds of networking abstractions, trying things out, and basically the agenda today is that I will give you a very brief introduction on why we are doing this to begin with, also to set up some or make concrete some concepts or some terms that we normally use when we are working on these Rust things. And then I will give a brief status update on the general status update of where we are in with Rust for Linux. And then Wexon will take over that and start with the proper tutorial where he will show you some of the things that he has been working on with very simple things that everybody can follow. No need to know Rust, no need to know really any particular details. So yeah, let's get started. So why we are doing this? Why we are doing Rust for Linux? So there is essentially the answer is we want to encapsulate unsafety, and I will explain what safe and unsafe here in this slide is. But the main thing that we are doing and the organization of the code that we have right now is that we have on one side, as you can see in the slide, drivers written in Rust. And then on the other side, we have the C APIs that you know of the kernel, all the C APIs of the kernel. Those APIs, from the perspective of Rust, are considered unsafe. But what we want is, rather than write drivers that directly talk to those APIs and see, which is possible, and it could be an approach that could be taken. And with that approach, you would get some advantages already from the language, things that Rust offers, such as enum types and many other things, pattern matching and many other things that really we don't have in C, encapsulation, etc., etc. But the main thing and why we are doing this is encapsulating unsafety. So what we do is we introduce a layer in between, that thing that you see there, safe abstractions, which are written in Rust. They talk directly to the C APIs, and then nobody else talks to them. So essentially the leaf modules, the drivers, things that are...
Hello, Miguel. We cannot hear you. Maybe you can check that if your microphone is working. No, and it seems it's actually not coming through. Yeah. It's not actually moving the 4 dots. Yeah.
Can you folks hear me?
Yeah, we can hear you.
Let's see.
Yeah, Miguel, you're on mute.
So while Miguel tries to fix his stuff, I can present this so we don't have to sit idle. So what Miguel was saying was basically that we want to build these abstractions between the C APIs and the drivers, right? He was saying that we can actually, if we wanted to, we could just allow the drivers to go straight to the C APIs. One problem we have with going straight to the C APIs is that they are considered by Rust unsafe, even though Rust can just call directly the C APIs. Hey, Miguel, are you back? We still can't hear you, man. No. So since these APIs, since we can call them directly, it would be okay. There would be no performance impact. The problem, though, is that they are considered unsafe. So if we were to use them directly, we would need these unsafe blocks within our leaf modules. Okay, let's see if Miguel is still can't hear you, Miguel. I can't. So what we decided to do, instead of allowing these drivers to go straight to the C APIs, we decided to create these safe abstractions between drivers and the C APIs. And what we want for these abstractions is that they are not only safe in the sense that they expose a safe API to the drivers so that they don't have to use these unsafe blocks. But also we want them to be zero cost, right? So the idea is that drivers would just use the safe subset of the language. I think Miguel intended to talk a little bit more about safety, and we'll see it in the next slides. But we would just use that subset of the language. We would guarantee that we have no undefined behavior, and it would all be zero cost. That's basically what we are striving for, is to build these zero cost safe abstractions that modules can use. And then if the end result of this is that if modules don't have any unsafe blocks in them, and that's what we want to do, and that's the examples that we're going to show today are going to be of this kind, with no unsafe blocks. Then if we exclude potential bugs on the C side or bugs in the abstractions that we built, then there will be no undefined behavior in these modules. So it's the idea is that people can write these modules and they can do it without as much fear as one would have if we're doing it in C, in terms of introducing potential undefined behavior and memory safety issues. Let's see if Miguel is back now.
Well, now.
Yes.
That's
yes.
more now.
Okay.
I rebooted the entire browser. Okay, sorry guys. So let's. I guess you talked about this slide already for a while, so maybe we move forward. Yeah. So we have two key concepts which you saw in the previous slide, which is essentially we have safe functions and unsafe functions. And what this means is what Wesson was just saying when I joined the room. Safe functions are functions that, and this is simplified, okay? This is a simplified version, so we can go quick into the tutorial. But safe functions, what we call a safe function, is something that doesn't trigger undefined behavior. No matter how the caller uses that function or that API, they cannot introduce unsafe behavior with safe code, okay? And the other way around, an unsafe function is a function that is not safe. Now, when we have abstractions that are supposedly safe, but they are not, because we made a mistake in the code, in the abstractions, in the implementation of abstractions, we call that unsound, which is different. So we have safe, unsafe, and unsound. And when we, that's one of the key properties that we want, which is that abstractions are sound. That means that the things that we say are safe are actually safe. Let's put it that way, okay, in simple terms. Now, to give you a very concrete example to try to see what this is about, we have an example in the next slide. So we have this function in C, right? What is the input to these functions? What are the inputs to this function that make that create undefined behavior? Is there any? Is there not? So some of you probably can spot it right away. And the answer is that there are two cases where we have undefined behavior. If you can go to the next slide, please, Weston. Yeah, so we have the case, of course, where we we call the function with b equals 0, and then also the overflow or underflow behavior. So in Rust, this function will be called unsafe. Of course, in C, this is a normal function that we use all the time, right? We have functions that take pointers, for example. Functions that take pointers in Rust, in general, they are unsafe because as if you dereference the pointer and you don't know the validity of the pointer, not just that it's not that, but it's also basically that you have to know that you can dereference that pointer, right? Because you have to know it's valid. Normally, you trust the caller that it gives you a proper pointer, let's put it that way. And therefore, most C functions, for example, that take a pointer are unsafe. We would call them in Rust unsafe. In Rust, we have ways to essentially define safe functions. And more importantly, we have ways to talk to C APIs and wrap that unsafety, basically. So we use unsafe code inside the abstractions to talk to the C APIs because, for example, we have to, trust what a C API is doing or the return values, etc., etc. But then we expose to the Rust drivers this safe interface. And essentially what Wesson has done and what he's going to show you for the networking abstractions is that he has managed to, for the things we have wrapped, or he has wrapped, all the code in Rust is safe. So as long as abstractions are sound, as long as the abstractions are correct, it means that no matter what you write in your driver using those abstractions, the servers that we are going to see, you cannot introduce undefined behavior, which means, maybe Weston already said, but if not, I will repeat. It means we cannot introduce memory safety issues, like, for example, a heap use after free, or a stack use after free, or data races, or type confusion, etc., etc. So in the next slide, I think we go to the status update. Yes. So what is the status update for Rust for Linux? So I will give you some quick graphs, not to take too much time. We have a growing community. First of all, we have a lot of people that looks interested into Rust for Linux. We have been steadily growing. This is the graph for the mailing list since essentially the beginning. I took some samples, and this is the graph for Zulip, which is the chat. This is more detail. We have more than 500 users now in the Zulip chat, so we encourage you to join if you want to know more about it. And also importantly, as you see here, is we're growing the core team. We have now a team of experts, or in different areas, of course, that you see there. Some are maintainers, some are reviewers, and of course we have other people around that contribute, send patches, and so on and so forth. But what I try to what we try to point out here is that we have a growing community, a growing team, and what we need is to get even more people in the kernel to play with Rust, to play with the Rust support, and try to see what they can work on, if they like it, improve it, so that by the time we are ready to go into production with some of these things, we have more support basically across the kernel, more support in terms of human developers basically behind the effort. Also there you see the webpage, which is the next slide as well. So the webpage is something that we have been putting together in the last 9 months, something like that. We have been adding things over time. So there's a lot of information there. If you want to know more about the project, please go there, because we have a lot of things there, from how to contribute, the sponsors, instructions, sub-projects that we have, related projects, users. So we try to put everybody together. And we have more sub-pages coming from other projects that I will speak very briefly about. So in the next slide, we have the sponsors and the industry support. There are right now we have 2 sponsors, basically people that financially contribute to the project directly, ISRG and through OpenSSF and OpenSSF. Companies give money to OpenSSF, and then OpenSSF, as far as I understand, redirects the money to projects that they think are important for their vision or their mission. The other companies that we have there, the logos, are companies that have either supported us in the past or that they give engineering time. So basically, for example, Wetson works now at Microsoft, and he has some time allocated to work on Rust for Linux at Microsoft, which is great. It's what we want to see more of that. Also, we have other people in Google. Alice, for example, we have at Samsung. We have Andreas, for example, that has also some time to work on, or full time to work on Rust for Linux. And then other companies that we have here are companies that have publicly supported us, and you can see the full statements of their support in the webpage. Then the related projects, and this is the end of this part, basically. So we have other projects that are important to know about, and that if you want to know more about, you should check out. For example, the GCC support. One question is when we will be able to compile kernels properly, because we have right now best effort support, just an very experimental thing, where we wanted to prove that it's possible to compile a kernel, at least the C side with C, and then the Rust side with through LLVM, and it works, at least for some configuration, but that's really experimental. It's not meant to be put into production at all. And what we want to do eventually is when those 2 projects that you see there, the first 2 projects, GCC Rust and the Rust C CodeGen GCC, are ready, we want to do, what we want to support is full kernels built with GCC, both in the Rust side and in the C side. So the first one is essentially a backend in Rust C, in the main Rust compiler, which means they, instead of just emitting code, intermediate code, which goes to LLVM, it goes to GCC. That already compiles and boots, or QEMU boots the mainline kernel without changes. This is a recent development, but Anthony is getting very close to essentially manage to give us a full GCC compiled kernel. Now, of course, this is still experimental. It's still early days, but the point is, hopefully, we can start to integrate this in the CI, either kernel side or the Rust CI, etc., etc. Then we have GCC Rust. GCC, this is the front end in GCC, in the actual GCC compiler for Rust. So this is developed from scratch, a new front end, and they have started to upstream in the current release. It's already, there is some code already there, but they plan the initial release that they want people to play with it, for the next one, 14.1. And then we have Kernel for Rust. It has been recently announced. So exactly the same, semantic patches for Rust, just the same way, basically very similar to what you know in the kernel for C. You will be able to use it for Rust. You can already play with it if you go to the repo and check it out. And then about the things that we have actually done in the kernel, if you want some come, yeah, thank you. So things that we have upstreamed in the last cycle. So we started in 6.1. We have been adding in the 6.2 some basic types, fundamental things, because the initial release, the initial merge was really, really basic. We were asked to cut everything down as much as possible. So we really cut it down to the very, very minimum that could be that could make some sense. So in 6.2 we added some types and macros and really essential stuff. Then we have in 6.3 arc borrow, other types, scope guard. These are types that are also fundamental to keep reference counts, etc., etc. Then 6.4, we have the pin-init API that is meant to solve the problem of of structures that are self-referential, basically, or that cannot be moved in memory because you would break the data structure. So that allows us to basically solve the problem with safe code instead of unsafe. So you could do it in unsafe with unsafe code, but with this API, it's very easy to write code that is safe. So you cannot basically mess it up and create a problem there. Other types, as you see there. Then in 6.5, we have the first Rust upgrade because we kept the compiler the same, but now we have a policy of incrementing the compiler basically we track the latest release. So we started there. Then 6.6, we have the main feature, I guess, is we have some pin-init features there in that release. We have also an upgrade, but the main thing was the Rust documentation test. We run them now through KUnit. So when you put the kernel, for example, or if you run KUnit manually, we take the Rust documentation test, which are code that you write, for example, for your users, and that runs as a KUnit test. So not only it's compiled, and you know that that code is maintained properly because it has to compile, but also it actually runs in the kernel, and you can use the APIs in the kernel, your abstractions, etc. Then in 6.7, just merged, I think today in the morning or yesterday, Linus took the PR, and we have the working abstractions is the main point, which Alice and Wesson worked on. So they are there. And then, of course, we have a lot of archives, a lot of work in progress things, either in the mailing list or in other repos or in private. For example, Binder, the NVMe driver, the DRM, the GPU, the Apple GPU driver, the VFS abstractions with a couple of example file systems, StarFS and PassFS, Phi for Netdev, mitigations work, etc., etc. So there is a lot of things going on all over the place, and we want that all of you join in the working side if possible to try. And with this, I'll leave it to Wesson, which again has worked a lot on this to manage to get you safe abstractions. So again, basically in the code that you are going to see in the Rust side, you cannot mess it up with respect to memory safety issues. Of course, modulo, compiler bugs, mistakes in the abstractions that we could still have there, etc. But the main point is you will see the comparison. And not only that, if I can spoil you a bit, the code is much simpler, if I may say so. So, and then we will go through async, which is really cool, and Wesson managed also to give us that on the kernel side, on the kernel, not just on user space where you may have seen it before, but also on kernel space. So, yeah, thank you.
Yeah, thanks, Miguel. One thing that I should say is that if you have questions as we go through the slides and the tutorial, I'd be happy to try to answer them. So if you have questions to Miguel, now would be a good time to ask, because now we're going to switch gears a little bit to actual code. But before we actually start going into the code itself, I'll give you a little bit of the status on networking support in the kernel for us in general. We have this chicken and egg problem. where the policy in the kernel is, and we understand it's rightfully so, that if there are no users for some code, then that code should not be in the kernel, basically. But then on the other side, on the other hand, we actually have users waiting for these abstractions to become available before they can actually spend the time to write the code. So we have this problem on one hand. We need the users of the APIs, and on the other hand, the users of the APIs want to see the APIs first before they invest time in using them. So for networking, we actually have some patches that enable writing networking sockets. So the thing we're going to show here is basically socket handling in the kernel. We have patches for this in the Rust branch, and we are waiting for actual users to show up before we start upstreaming these, right? So this will be parked there basically before we until we find users. And there are some cases that we have in mind that have spoken to us. So we can talk about that later. So for this tutorial, what I did was I actually got to the latest version of the kernel from last week. So it's 6.6, and I got some patches from the Rust branch applied to it, and that's the kernel that we're going to be using for this tutorial. And what we're going to be doing in this tutorial is basically we're going to write an echo server on the kernel that runs in the kernel. It's a trivial server. All it does is it's actually listening on a port, and as connections are accepted, it has this. It creates on the synchronous version, it creates a thread for each connection, and then as data arrives, it writes back the data. It echoes the data back that it reads. Right. And the reason we chose this trivial server is because a lot of kernel code that does this have similar requirements in terms of how they want to wait, how they want to manage threading, and having the simple driver actually allows us to look at these aspects and not get lost in irrelevant details about parsing packets. Not really irrelevant, but like not generic problems, like specific to each protocol. So what we're going to do is we're going to start with a very simple version, which is synchronous, right? And then for each connection that arrives, we create a new thread, and we'll have code in that thread to handle that. And we're going to do step by step that. And what I'm going to do is I'm going to alternate between the slides and our console here, and I'll write the code. And if you want to follow, there's a link there, and I think Buchun just pasted the link to the kernel, but there's also a link to the code. It's on GitHub. But yeah, so we start with that, and then we're going to switch. And then we'll talk about the problems of that. It's not scalable, basically. So we'll migrate the C version of that to be asynchronous, and then the Rust version. And this is a bit of a spoiler that Miguel sort of gave it already. Is that there's not a whole lot of difference between the synchronous and asynchronous versions of the Rust code, but in C you'll see that it's quite different. Okay, so let's get started. The first slide. Should I change this? Yeah. The first slide here, and this is actually the theme we're going to follow. We're going to have the C side on the left, and the Rust side. Yeah, okay. Somebody's thanking Buchun for the links. So on the left side we have the C code, and on the right side we have Rust code, right? So we start with an empty module, and it's unloadable. There's not a whole lot to remark here. I've shown this sort of thing in a bunch of other different presentations. But just to recap, what we have to do in Rust is we have to declare a type.
Wait.
In our case is, yep. Is there a question?
Can you hear me? Yeah,
Yes.
okay. No, sorry, we lost you for a bit, for about 30 seconds. You can go ahead. Go ahead.
Okay.
Just go ahead. We lost you for about 30 seconds.
It was fine for me.
But you couldn't see the slide.
It was fine
We
for me.
couldn't see the slide, but
So, yeah.
Okay.
I'm sorry.
It was fine for me here. I could hear Wesson all the time,
Okay.
so I don't know.
No, we could hear him, but we couldn't see the slide for about 30 seconds. But please proceed.
Okay.
Yes. All right. So So what we need to do on the Rust side is we need to declare a type. In our case here is echo server, and in our case for the empty module, it doesn't have any state associated with it. It's just a type, just a struct, an empty struct, right? And then we have to implement this kernel module trait for that type, and the only function that is required is an init function. And in our case, we just succeed the request, which is similar to the C side in the sense that it just succeeds here, returning 0. Right? We don't actually need an explicit exit path. So what happens in Rust is that when a module is unloaded, the instance of this echo server that was returned in this result here gets dropped. And the consequence of that is that if you implement the drop trait, so if you want to customize the behavior, you can implement the drop trait, and then your code will run when the module gets unloaded. In our case, in our particular case, we'll see that, and this is a little bit of a spoiler too, we actually don't need to do that. All the cleanup code actually happens automatically by drop implementations of things that we use directly. So here's the two modules. In Rust we also have this macro here where we say, oh, we're defining a module, we give it a name. This is a name that we use when we do PR info, PR error, and those things. This is the type that is to implement the module. We have to give a license, similar to the C side, where we also need to give a license. So what I'm going to do is I'm going to switch here to this. Oh, I think it's quite small. Let me switch the size here. Is this readable? Is this good enough?
Yeah, for me it is. Yeah.
Okay. What I have here. Okay, let me see this. Okay. So in the samples, I actually have a bunch of steps. You see here. So this is step 1. So this is the code that I had just showed you. But then what I'm going to do really is actually I think I already did that. Oh, what's going on? I don't. Oh yeah, okay, came back. What I did is I actually created a work.rs file, which is basically a copy of that, and this is the file that we're going to change. Okay. So I'm going to do a make here, and we don't have any modules loaded, but I'm going to do an ins mod on that work mod. Okay. So we do that. The only thing that we can really see is that the module is loaded here. It doesn't really do anything for us yet. We can remove it, and you see if you do ls mod again, it's not there anymore. So what we have in this basic server is that we can load it and unload it, and nothing happens. It's similar to what the C side would do. In fact, if you look at the code, we have the same thing on the C side. I did that here too. So you have the code here. So if you want to play with it later, you can play with both. Let's come back to the C side, and let's go back to the slides. Actually, here I think I'm missing some stuff here in the bottom. But anyway, let's go back. So that was the first step. Okay, the first step was just to have an empty module. The next thing we're going to do as part of writing our server, our echo server, is to create a listener thread. Okay, and we see here both on the slide again. On the left we have the C code, and on the right we have the Rust code. So what I'm going to do now is, since there is no requirement for people to know Rust, what I'll attempt to do now here is I'll show you some foot guns and areas where the C compiler lets people make mistakes and potentially lead to memory safety issues or undefined behavior in general, and where Rust prevents that. Okay, so the first thing is here. When we actually create a thread, it takes one argument on the C side, and the argument is void star, right? So you're actually losing the type. In our case, specifically here, we're not passing anything yet, but we'll see later we're going to pass a socket. The problem that C may have here is that if you specify a type here that gets cast to void star, and on the actual thread you cast it from void star to a different type, then you have type safety issues and potentially memory safety as well. Here in create thread, actually, before I go into the create thread, I'll show here that on the Rust side, we call echo listener. So what the task spawn function does is it takes a closure, right, to run, right? So the closure doesn't take any arguments, and then you call the echo listener in this case, which is the same echo listener that we have on the Rust side. But here we can actually specify whatever arguments we want, and they'll be captured from the context here, right? So this is all typed, and we'll see later that it's also typed on the Rust side. When you create a thread, you can also name it, and on the C side we have printf style formatting, which you can also mess up, right? You can say that it's a pointer to something and press an integer, for example, and then you mess things up. In Rust we have this fmt macro, and it's type safe, right? So if you try to do something here that would lead to undefined behavior or memory and safety, you get a compile time error. Another thing that we have in C is that you actually need to do explicit error handling, and if you forget to do the error handling, nothing really happens. In Rust, task spawn can fail, and the way we're handling errors here is with this question mark. Okay, what this question mark says is if this actually fails, then we want to return an error right away. Basically, this is a syntactic trigger for that, and then we run the structures of anything that we might have created in between. But if we actually forget to do this question mark here, task itself would not be a task. It would be like the result of trying to create a task. So you wouldn't be able to handle the task itself. So you're forced to do that. And in fact, if you didn't assign to a task, you would actually get a compile time error saying, the result of task spawn must be used, and you're not using this. So again, another way in which, and this is actually the idea that not being able to use the task before you check the result is actually fundamental to memory safety, because if the thing failed, then it returns not a task, return null or something else, then it's not a valid task. And you try to use it as a task, you'd get some undefined behavior. Another footgun that we have on the C side, in general in the kernel, is that we have this mixing of pointers and error codes, right? And this is a footgun because one might actually check that the result of create a k-create thread is non-null, for example, which is actually not an unusual pattern, right? If you call a function that returns a pointer, usually what you have to do is have to check if this pointer is non-null, and there are examples like K-malloc and a bunch of other examples that work this way. But there are also another subset of functions that don't work this way. They just encode errors as pointers, right? So you have to use this is_error macro, right? And it's not clear when that is the case. So this is something that C allows, and Rust doesn't allow you to do that, right? Rust has this enum types. So when you get back a task, it's either going to be an OK or an error, right? There's no way for you to ever confuse the two. Another footgun that we have in this small example here of just creating the thread on the C side is that the thread that k-create thread returns, once you wake it up, right? If the thread exits, the task that it returns actually gets its ref counter decremented and maybe freed. So what you have to do is you actually have to increment the ref count. And you forget to do that and try to touch T after the thread exits, then you touch invalid memory. It's a use after free. So this is another footgun, and in Rust, of course, we don't allow this. The task that gets returned is a ref counted task. Another thing that we have to be careful about on the C side is that when we are unloading the module, we actually have to tell that thread to stop, right? If we don't tell it to stop and we just let the unload of the module happen, then the next time that thread runs, it's going to run on unloaded code, and you're going to crash the kernel. What we do in Rust is that we have this K task, which is really what's returned by spawn. And what it does is, when it goes out of scope, it actually automatically tells the thread to stop. And so what we did here, actually, which is slightly different from what we did in the previous step, is that we encode this. We actually return this as our state. The task, the thread that we created is our state, which means that the thread remains alive as the kernel, as long as the kernel as the kernel module is loaded. And once the kernel module is unloaded, it automatically goes away. And then the last thing here is that you have to remember to actually decrement the ref count that you had incremented before here, because if you don't do that, you are of course leaking memory, leaking the task on the C side, right? And in Rust we don't have that. We as this K tag is dropped and destroyed, we automatically ask it to stop, and then we decrement the ref count, and it's not accessible anymore after that. So this is our second step. Let me see how we're doing on time. Let's switch to the code. So instead of actually typing the code here, I'm just going to open it this way, so we can go a bit faster. So what we see here is the code that I have here, but expanded, right? So this is the pieces that changed between this and the previous step. But if you look here, we also have the echo listener, which is an empty function, a function that takes no arguments and just returns. And everything is in one line, so it's actually easier to read. If we actually try to load this, step 2. So we see it loaded. But since our thread actually doesn't do anything, it comes out immediately. So we can't really see what's happening. We'll see later that we can do a PS and actually find this on the thread. Because we actually hear you when you type. If you could mute, I think it would be better. Yeah, thanks. Yeah, so now my screen is actually. Oh, now I can see the thing in the bottom. So let's come back to the code. We still have it here in a less mode. Let's unload step 2. So the next step. So now we created the thread. So what we want to do really is we want to create a listening thread, a listening socket, right, and send it to that thread. So the thread can loop, waiting for connections to arrive. And here we have on the left the C code, and on the right the Rust code. I will point out some mistakes that can be made on the Rust side. Here on the C side, on the port, we actually have to do a host to network.
Yeah, it's on. We are.
Yeah, let's see. Maybe
We're kind of losing you there. Can you hear us? Miguel, can you hear us? We can see you more.
Yeah, I can hear you.
Okay.
I think he has briefly lost.
Yeah, he doesn't know we.
Sorry for all these troubles. Sorry everyone for all these troubles. Let's see.
Yeah, this is why we want pre-recorded talks if you're not showing up here.
Yeah, but we couldn't do a pre-record as we agreed.
Yeah, no, well, not you. I mean, I'm talking to the crowd here.
Yeah. I know. It's he's presenting slides. Let me see. Maybe I can.
So Miguel, we're waiting for Weston. I was more excited. I wanted to see how you butcher SKBs, but there's no mention of SKBs or anything in this tutorial.
No, we are going through in the tutorial. What we are going to do, just to give you some more context. Meanwhile, Watson comes, so we can maybe go faster later. So what we are going to do, let me see. The networking part. Let me see 1 second. I hope I don't crash my browser by trying to do this.
So anybody has a question, offline, remote or local, while we wait? I think we got Watson back, yeah.
Yeah, Watson. Yeah, Watson, we see you. Maybe you can disable. I would recommend maybe disabling the webcam so that you have less bandwidth to, I guess.
There's a question there for you. Yes, I don't know if you can see the question or you want me to read it for
you. So Botion, I think, already replied on the comments. Echo server here is a type representing driver. If there are multiple instances of the same driver, I would expect there is another type representing that, say, foo device, then remove can be handled by the drop of foo device. Yes, we have. This is a basic support for things that have, you have to handle different devices, you have to handle different things in your driver. That can be done. I mean, it's of course it has to be possible to do that. We are not showing it here. I don't know if Wesson has implemented that for that networking part. I don't know, but we for sure we have to handle that. And we have discussion in the main list about similar. There is another question. 1 second.
Hey, can you folks hear me?
Yeah, maybe don't enable the webcam to try to reduce the bandwidth, Wesson. Meanwhile, you present, I am answering a couple questions. Can you show a little bit of how bindings for specific things are added to get from Rust to C? It is doable with limited Rust skills, especially since the beginning. There will be lots of things that don't have them yet. So writing the abstractions is for better or worse. The reality is that is the hard part of writing Rust in the kernel. Writing the abstractions requires basically knowing, or maybe not being an expert, but at least you need to know, have a solid knowledge of what is unsafe in Rust, what things can you do, what things you cannot do, with references, what are the guarantees that references, mutable reference or exclusive references give you in Rust, etc., etc. You have to really know what you are doing on the FFI layer, and so on and so forth. So yeah, if you are now, having said that, it doesn't mean you cannot play around with it. I mean, you can play around with it, you can write it. It's not hard in that sense to write abstractions. It's rather the getting to the point where you have a sound abstraction, where you know, or you can more or less prove in between quotes, you can show, or you have an argument of why nobody writing safe code calling you through your safe APIs can break basically your memory safety. So getting to the point where you have sound abstractions is the hard part. This is what I was saying. Now, if you only care about, playing around, just doing abstractions that you think maybe are sound, maybe you are not an expert on that particular piece, because you also, in order to write sound abstractions, you also have to be normally an expert on the C APIs, or at least you have to really know well what the C code is doing, because normally you are relying on some of the properties or the invariants or post conditions that the C code gives you, right? So in order to write sound abstractions, you have to do that. Have knowledge on both sides. That's why we need more maintainers of the systems. The actual maintainers, the actual experts of the different systems. We know them. We need them to write these kind of abstractions and review them. We can help in the beginning with the Rust part, but in the end, in order to scale, people will need to learn the Rust in order to maintain that code. So I think Weston is back. Yeah, I think it's okay now. Yeah.
So I'll answer that part of that first question that I see here. If we have remove in addition to module exit, and the answer is yes. So basically the cleanup for these things happen on the drop of these types. In fact, we've heard loud and clear from maintainers like Greg KH that module unload is not really a priority. So the guarantees that we offer here are actually when you never unload, right? If you do unload, you need to do a few things extra, and there's a slide later on what needs to happen. But the remove is actually what is guaranteed to not have any undefined behavior on the Rust side. So sorry for the technical difficulties here. The message that I got here was that I was disconnected. So I'm back now. Anyway, so what I was talking about here in this slide was that the kernel bind API, actually what it takes is a sock header pointer. But with passing is actually different. It depends on what kind of family you have. And each family has its own type. And the way you do it in C is you declare the type that you really mean, and you initialize it like I have down here. And then you cast it here. But of course, this actually this allows people to make mistakes. Okay, and it's also not discoverable. You don't really know what kinds of types you are allowed to use. So on the Rust side, it may look a little verbose. And actually, I thought it was a little verbose when I first did this, and it is. But if you compare to the C side, it's less verbose in the sense that you can initialize this in one shot, and you cannot mix things, right? So what we're saying here is we want to create a socket address, okay? But a socket address may have several instances, and you have several types. Like you have v4 and v6 and Unix domain sockets. And so in our case here, we want a v4 address, socket address. And then to create a v4 socket address, what we need is to specify the address we want. And in our case, it's any and the port, right? And you see we have no conversion of endianness here. But we could do like, so if, for example, we were to mess this up and we would put like a v6 here, for example, the types of these arguments would be wrong and would just be rejected. So we actually have type safety. And then when we create the listener down here, it's called TCP listener, and we pass in the address, right? And the address actually dictates what type of socket is being created, right? Which is not the case here on the C side. On the C side, you create the socket independently. It's covered here, but let me go back. So you see like AFINet. So if you created the AFINet socket, you need to specify a AFINet family. On the Rust side, we sort of elide this socket creation, and it's part of this try new, and it takes an address, and based on the address, it knows what kind of socket it needs to create. And we actually fused all three of these APIs into one here. So it creates the socket, it binds, and it listens automatically. But this, of course, can like the fusing can be done on the C side too. There's nothing special there. But what we avoid here is this casting and potential errors that people can make. Another thing that I mentioned before, we had a null here when we created the thread, but here we actually specify a socket, right? So the type of socket is a struct socket, and then it gets cast to void star here, which is also potentially a problem. And here we have explicit error paths with go-to statements on the C side, right? You have to call these functions, and then if something fails, the reason we have this go-to here is because we want to release the socket and then return. In this case, it's somewhat simple. We have more complicated cases on the C side in general in the kernel, where if you had multiple resources that we had to free, this would be basically a stack of cleaning up in reverse order, basically the things that had initialized. And if you look here on the Rust side, we don't really have any explicit error checking like this. What we have is we have these question marks, right? We have a question mark here, and we have a question mark here, right? So what it means here is that if the socket creation fails here, if we're trying to create a listener and it fails, we just return right away, okay? Which is basically something like this. If it fails, we return right away, okay? But here we have the question mark later, right? On the Rust side, if the thread creation fails, what we have to do is we actually have to clean up this listener. We have to release the socket, right? But as I said, we actually have the drop implementation for TCP listener actually closes the socket. So we don't actually need to explicitly close it. We know that if we do an early return and we don't consume it anywhere, then it will get released automatically for us. So it actually saves us the need to do all this error checking. And you see it's more streamlined here. It's a bit hard to read here on the slides because I had to break these lines to make it fit on the slides. But when we go to the code, you'll see that it's actually quite straightforward. Another example that may be problematic in the error code. Now, in all of these error paths, we assign the ret first, and then if ret contains an error, we use goto. But here, the error is actually encoded in T, right? So if we actually forget to assign the value of ret here, just to a goto error sock like we had here, this actually is going to return 0, and it's going to return success, but it should have failed. So another footnote here that we have in C that we don't have in Rust. We always return the error code because that's what this question mark does. So step 4, but before we go to step 4, I'll show you the code and we'll run it, and you'll see that with that stat, that when we load this model, we actually have a list. So this is step 3. We won't be able to see the listener yet because this is one thing that is happening. When we call listener and we ask listener to this thread, a separate thread, it comes in. Right? Since it's empty, what happens is that the drop implementation of TCP listener is going to be called, and then the socket is going to be destroyed. So we actually won't be able to see it. We'll see it on the next step. This code that I was showing you before, and here it's a bit easier to read because it's all in, like each statement is in one line, right? So we create the address that we want to listen in. It's any address IPv4 on this port, and we create the listener. We use the namespace of init. We pass the address, and then we spawn the task, and we call it a listener task. And this is the function that the thread is going to execute. And we see here that it's all typed, right? On the C side, this was untyped. It was a void star that had to be cast in the listener, right? And here it's typed. There is no potential for you to make mistakes here. If we actually go to step 3 on the C side, here's what we get. When we call create thread, we pass sock, which is struct socket. That's what we see here. But if you look at the actual thread, it takes a void star, and we have to do a cast here. And this is actually a potential source of mistakes, and we have to release the socket and return 0, return success in this case. So there's a bit more code on the Rust side and on the C side, and potential to make mistakes here with the times. So we actually here, when we show this sort of stuff to people, and they say, oh no, but this is clearly safe because I've checked that the type that I'm passing here is the type that I'm converting here. So what you guys are saying, what you Rust folks are saying, that it's unsafe, it's not really, because I've checked, right? But to clarify what we're trying to say is, if you actually come here and you change the type because you updated the code, the next person who's maintaining the code updates the code and passes something else here, like a struct that contains the socket plus some extra information that you want to pass, right? And the person forgets to update this, right? The compiler is not going to complain, right? The compiler is just going to compile it and you're going to run, right? And then you're going to have a pointer here to the wrong type, and then you have potentially undefined behavior at runtime, right? So what we're saying is, if you do this on the Rust side, the Rust compiler will complain, right? So if you come here and you call echo listener and you pass it a different type from what's expected here in the function declaration, the compiler will fail compilation. So this is what we're talking about when we say about unsafe potential undefined behavior there. So that's step 3. Okay, so we have the listener thread created, but we were not doing anything there yet. And here's what we have in step 4. We actually call an accept to accept connections on that socket that we create, the listening socket, and then we're going to create another thread to handle the connection that we've just accepted. Here's the code on the C side, and here's the same code on the Rust side. This is the thing that I talked about, in the code. There's an implicit cast here, maybe a source of problem. The same thing happening here. If you're creating a new thread and we're passing again a socket, right? That guy has the same issue. It takes a void star and needs to convert it to socket when it accepts it. We also have here an explicit error check and error handling. If we fail to create the thread, then we just close the socket. Basically, we release the new socket that we've just accepted. And this is also something that I showed before. When we want to finish the listener, when we ask it to stop, we need to close the socket that we were listening on. And if we fail to do this, the socket will remain open in the kernel, and it's going to be a leak. And clients connecting may be able to feel its queue. And then on the Rust side, if you look here on the right, we used a bit of a functional style of doing things. And the reason it's done this way here is because we actually don't want to fail the whole function if the creation of this thread or the acceptance of a new connection fails. We want to continue. So we basically want to, on success, we want to do a few things, and otherwise we just want to keep on going. So what we do is we call accept on the listener, and this one argument here is telling us whether we want to block or not, right? And we say true, like we want to block, right? If there are no connections, we want this call to block. And then what this and then does is, if it succeeds, then do this, right? If it fails, then this doesn't happen, right? But if it succeeds, then what the return value of accept is another. It's a connection, right? It's a TCP stream, right? So, and then what we want to do it with what we want to do with it is we want to spawn a new task, a new thread, and give it a name, and we call echo handler. It's the same name that we have here on the C side. And if that succeeds, then we want to detach. And this step we don't have it on the C side. And the reason we have this step here on the Rust side is, if you recall, what I said was that the tasks that we create, we automatically, when they get dropped, we automatically wait for them to finish, and then we close it, right? So, and this is not what we want to do. What we want to do is we want it to continue to run, right? So what this detach does is exactly that. It says, okay, continue to run. When it goes out of scope, don't stop it, basically. And the reason we have this let underscore equals here is because since this actually may return an error, if we don't assign it to something, then the compiler is going to say, oh, this guy may fail when you're not handling the error. So this is basically the handling. We say we want to ignore. If it fails, it's okay. Just keep on going. Try to accept the next connection. Here we have an alternative step. If this is too functional style, this may be too functional for some folks. So this is a more procedural sort of way of doing things. We call accept, and we say if the return of that is okay, and we have a TCP stream here, then spawn a new task. And if they succeeded, if the spawn succeeded, then detach. Right? This is essentially the same as what we had in the previous slide. I feel this is a bit more compact, but maybe too cryptic for some. So let's look here in step 4. This is how the code looks in step 4, and you see it's I feel a bit more readable because it's all in one line. And again, the echo handler doesn't really do anything. It takes a TCP stream as argument, doesn't do anything, which means that the thread goes away and the connection gets closed, right? So now, if we actually load this guy, we should be able to see the listening, and we should be able to connect, although we won't get the echo just yet. So let's try that. Let's do an ismod step 4. it's loaded. If we do a netstat, we see that we are listening on port 8080, which is the port that we specified there, and we can try to connect that port, and it's connected. And if we try to send something, it just comes back because the connection gets closed. But see, now we see some signs of life from our module. And then if we unload step 4, let's do netstat again without listening on that port anymore, and lsmod doesn't show it. So I'll just emphasize again the cleanup, right? If you look here, what we're doing is we are listener and we are exporting a task to listen. And that's it. We have no cleanup anywhere here, right? But as you could see, we actually stopped listening on the socket when we unload the module, right? And we didn't have to write explicit cleanup code anywhere ourselves. And if you look here, I'm actually using the functional style to do the echo listener. So let's go to the, since we're getting short in time, let's go to the next step, which is actually the function that will read through the contents of the contents that are sent by the peer and echo them back, right? Here, Rust side is the C side is a bit in disadvantage because it has the receive message and send message only. It doesn't really have a send and pure send and receive. So there's a bit of extra code in here, but it's not really a big problem. There are some issues like when we are calling receive message, we specify the flags here as an extra argument, right? But then when we're calling send message, there is no extra argument here for the flags because the flags are actually now encoded in the message header, right? Because message header is an input argument for send and it's an output argument in receive. So there's some potential for confusion here that Rust doesn't have. It's very clear in Rust what's input and what needs to be initialized and what doesn't. But this is actually simple straight line code, right? You have a thread. It has a for loop, an infinite loop that receives some message into a buffer, and then there's an inner loop here that sends back, right? And the reason we need this inner loop here is because when it's TCP, when we are sending messages, we may not send the whole thing that we requested, right? It may send maybe a partial send, so we have to make sure that we send everything. That's why we have this loop here. And if you look at the Rust code, it's also quite straightforward. I actually omitted some declarations here to make it fit and be more readable on the slides. But in Rust, I didn't omit anything. All the code is here, right? So what we do is we do a read and we have a question mark. If it fails, we return right away. We have a comparison for 0, meaning that the connection was closed, and in that case, we just return OK, we succeeded. Otherwise, we have this loop that writes back basically, and again, it may be a partial write, so we update what we're trying to send. So this is the actual echo code. So let's go back to let's come here to step 5. This is that same code now like in longer form. We had to change this a little bit because now echo handler can return an error code. So we have to say here that we don't care about the error code. And that was it. Everything else is the same. We don't have any explicit error handling anywhere. But let's try to insmod on this step 5. So next stat, we see port 8080. Then we can connect that, and then if we try to type something, it goes back, right? And if you do Control D, the kernel it disconnects. And if you do that, we see a connection here in time space. And then the last step for this synchronous version is that we want to not allow the module to be unloaded while we have a connection, right? So I'll actually go quickly here. There's a foot gun on the C side. that if you don't call this function, if you just call module put, for example, so basically what we have to do is we have to increment the ref count. When the thread finishes, we need to decrement that. And if we decrement it here, then the code may be unloaded, and then you return to the code that has been unloaded. So there's a potential problem here. So we have to call this function that actually decrements the thing and then exits the thread. We have explicit error handling again here. And then here, since we have two resources to free, we actually have to do the module put here to undo the get, and we have to release the socket, which we don't really have to do on the Rust side. What we do in the Rust side is we call this variant span with module, and it just like everything else. But since we need to pass a module, we need to change the init to actually pass the module as an argument. This is the extra argument we have here. We are going to be short in time, so I'm going to skip.
Watson? One thing they told me, yeah, we have about 7 minutes, and there is a question about the detach that probably you want to answer, because I know that you wanted to emphasize that. Is the t.detach safe? Yeah, the question is there. What if we remove the module while still having threads run?
Yes. Okay. So this actually is relevant to this step here. So what we heard from Greg KH, as I said before, was that the module unloading is not something that is to be used in production, and then all the bugs that we found and reported were basically not fixed. So we actually don't try to enforce it, right? The very safe guarantees that we offer are related to when you don't unload the module, right? So if you actually want to unload the module, there are a few things that you need to do. For example, in here you have to do the spawn with module, right? This will actually increment the ref count and prevent it from being unloaded. But then even when we do it this way, we claim that it's a bit nicer and has fewer footguns than the C-side because of this. And I can show it really quickly what happens. Do I still have step 5? Let me remove step 5 here. Let's insert step 6, which is actually the last one for the synchronous one. And then let's show next step. Make sure that it's listening. Now I'll open a connection to that. Okay, so now I have an extra thread, and here I'm going to do Control Z. So the connection is still open. If we do net stat, shoot, I didn't mean to do NC. I meant to do net stat. If we do net stat, we see a established connection here. And if we do ls mod, we see that it's used by 1 here. So if we actually try to unload step 6, it's going to say it's in use. So if we do FG to go back to our connection, so you see it's still alive, you can still get the echoes. And if you do Control D to disconnect from it, and now we try, actually let's do ls mod again. You'll find the use by is 0. So now if we try to unload, now it succeeds. All right, do ls mod, it's unloaded. Right, so we actually have support for this, but it's not something we worry about. Basically, you have to do a few steps, like you had to do the spawn with module here for this to succeed. And since we're almost out of time, the problem with this solution is that we create a thread for each connection that we accept, and the problem with that is it doesn't scale, right? If you're actually writing a real server and we want to handle lots and lots of connections, this is not an acceptable solution. So what we need to do is we need to create this state that holds a connection state, and we have to have the state machine that drives this state. And in the samples you'll find a C version, and I actually had in the slides here a description of what it does. So we have a description of a connection, but I'll just rush through it. Here's the state machine, right? So we have a state machine where it says if it's reading, then do the read, and then potentially change the state to is reading equals to false, and what we have to write. And then if it's not reading, then it's writing, right? Then we send a write, and we update our states, and we conditionally change the state back to is reading once we send everything. And remember, this is the simple echo server, right? And we have this state machine with just 2 states, one in which we are reading another one in which we are writing. For more complicated scenarios, the state machine is much more complicated, and you'll find this in SMBD and NVMET. And we need to hook the sockets for notifications when things change. We have to check mask, and we didn't check the mask in the example. So we have to keep track of the connection so that when we unload, we free them up. And here's the C code. I'll just skip through it because the highlight of the talk is this. So we have to do all of this on the C code, which makes the code scalable, and which is great, works very well, but it's very complicated, right? To switch Rust to do this same thing, here's what we have to do. Here's how we build the state machine. Originally we had just a function. We put async in front of it, right? So now instead of declaring just a regular function, Rust is going to create for us a state machine, right? And then in the places where we would normally potentially block, we actually have to do this dot await thing that tells Rust that this is a point where we may lose the CPU and we are in the work queue. Actually, I failed to say this, but this actually now runs in the work queue. And when we block at these points, then the work item actually stops executing, and the thread is free to do something else in these two places basically. And in the listener loop, we also make it async. And we use spawn task, and we pass the executor, which is the work queue executor, and when we are starting a new task for connection that was accepted, right? And then this actually just creates the state for this new connection, which is a block with the state machine. It's not a thread anymore, right? And the work queue is the one that manages the thing. And in module initialization, we create a work queue executor and we spawn the listener. That's it. So these 3 slides are the changes that we need to make to the Rust side for it to work in asynchronous mode, right? And this is actually what we wanted to emphasize. And in fact, this works better in the unload case because what this does is it automatically tears down the connections because now we keep track of them in this executor. So we actually, in this case, we don't really have to do anything else because the executor keeps track of all the connections we have and tears them down. So yeah, our time is up. I actually talked about async Rust and how this works, how the state machine is created. There's some diagrams of how the state is actually managed by Rust, and there's a link there if anyone wants to watch that. And I think that's it. I think that's time for us. Questions?
Okay. Yeah, questions?
Yeah.
Cool. Hi, I'm David, and first of all, I love Rust, and I love to be able to find more time to kind of contribute. Couple of points about this talk. The first one is I would have liked to seen more on one of the slides, earlier slides. You had a diagram of like wrapping unsafe C abstractions from the kernel. So let's say I'm writing a driver in networking, and I want to use things like the page pool. I want to use things like the kind of PCI APIs, and I want to do things like allocate like kernel data structures. I would have liked to seen more examples of that in your example, because we wouldn't ever write a like almost user space server in kernel.
Yeah. So for that, so our expectation for those things are actually that the maintainers of those subsystems will write these abstractions for us, right? And basically what we want is we want for them to actually look at the APIs that they regret having written and exposed and don't expose those on the Rust side. But we also want them to do these safe abstractions, right? It's like, is there a way for you to expose these things in a way that modules that want to use this won't get into trouble when they use this. There are cases when we can't do it, and in those cases we actually have to declare functions, for example, as unsafe, right? And then in those cases we actually put a section in the documentation that describes what the requirements are for this to be used safely. And then our expectation is that users in that case will also add a comment specifying how they satisfy those requirements. But a talk about creating these abstractions may be interesting, but this was not our here, because we actually need somebody to actually be somewhat experienced in Rust and in the subsystem, which actually makes it a bit harder to find. So in the beginning, what we're trying to do is we're trying to partner with maintainers, right? Like we'll get the maintainers' expertise on the subsystem that they maintain, and our experience in Rust and actually building some abstractions in Rust, and together we'll start with that, and then over time, people will develop Rust expertise we expect, and then just be able to do it themselves.
Yeah, that kind of leads to the second question, which is, how do you keep things in sync between the Rust API and the underlying C API? So is the expectation that maintainers need to themselves write the Rust abstractions and keep it up to date?
Yeah. So well, there are several layers to that question, but in short, yes, the maintainers are the ones in the kernel. Otherwise, it doesn't scale. The idea is that the subsystems in Rust, the abstractions basically, are maintained by the maintainers of the same code in C. So we are doing some of the abstractions now ourselves in order to bootstrap basically the support. And Weston has worked for 3 years essentially on making abstractions for different things and showcase how Rust looks. Basically to come today and show you, well, this is how your user code could look like, right? But now the abstractions, of course, we can give you the first versions. We can give you help there. We can work with the maintainers. But in the end, we want that things go through the tree of the subsystem of the maintainers. They take the patches, they handle the patches, they maintain the patches, and yes, they will need to keep it in sync with the Rust side. If you change a function substantially to the point that the post conditions are changing, or changes that matter from the Rust side, then you have to update the Rust side as well. So that's why we are trying to reach out, as Weston was explaining. We are trying to reach out to maintainers that are willing to start that process and to play with it, because we think that the advantages of having that and doing that wrapping is very, very nice. Because as you saw from Weston's code here, when all that is done, which is some work, right? After that, you can write drivers, as he was saying. He was showing the echo server is completely in safe Rust. It's shorter, it's safer in the sense that you can make less mistakes, including logic mistakes as well, because of, for example, the error handling, etc., using types, strong typing, etc. You will make less mistakes. You have to write less code in the leaf modules, and it's all safe. So Rust safe. What means is no memory safety issues, no users after free, etc., etc. So basically, that's the core advantage. But we need, of course, maintainers to start working with us, and some of them already did. For example, the KUnit maintainers, the working maintainers, or Tejun in this case for WorkU. Tejun took the patches yesterday, sent them to Linus yesterday through history, for example, for the WorkU abstractions. So that's
Matthew Wilcox also said he commits to updating both sides, the C and the Rust side of the abstractions for the page cache. Yeah,
which is great. Yeah, we need more maintainers like that. Basically, if everybody was like that, it would be very easy.
Yes, if we have maintainers in the room interested in doing this. Actually, even if you're not a maintainer, right? If you just if you're knowledgeable in some subsystem and want to build it, we would be glad to partner with you to build these abstractions. And then you may end up becoming the maintainer of the thing.
Thanks.
I have a question. I actually presented on the workshop for compilers, so my view was more on the idea of have you considered actually auto-generating those bindings through, let's say, using Clang's AST library as abstract syntax tree, matching of those declarations, for example, and actually generating Rust API directly from that?
So we do that through binding. It's a tool that takes uses Clang, libclang inside, right? Parses the C code and generates the bindings. But those are what we call bindings, like the low-level bindings. That's not what we are talking about. When we were discussing before, we were not talking about that kind of binding, which is what we call low-level bindings. We are talking about abstractions, which is actually where you call those bindings, and you make the thing safe, or the abstraction safe, so that nobody using it can break safety, memory safety.
So the idea is that there's actually some design that needs to happen, right? Between calling the C code and exposing the code to the Rust side. There's some design, there's some work that needs to happen there that cannot be easily automated. If you actually can find a way to automate that, it will be awesome, right? But
maybe an AI or something. But yes, it's not trivial to automate. It's not trivial. You cannot really automate it.
Yeah. I'm gonna have to cut it short. Sorry. We should have given you maybe 2 hours instead. Next conference. Bochun is here all day long. So you want to work on Rust? Talk to Bochun, sitting right there. Raise your hand, Roger. Yeah, that's him. I liked your statement there when you said I love Rust. It almost feels like you're in a AAA meeting. Okay. Thanks, everybody. Let's give them a hand of applause.
Thank you, everybody. I'm sorry for the technical difficulties on both ends. Sorry, not on both ends, on both cases. Sorry.
Both of us, yeah.
Yeah, both of us, yeah. Sorry.
Yeah, you did great. You did great. Thanks.
Please see the slides. Weston has more slides there for the async, and check the repo and compare the versions. And it's very nice to see.
Yeah. Bye, everyone. Thank you.
Thanks.